Hello everyone, Mr. Fawcett here, and we are back with another geometry lesson. We're actually combining two lessons into one here, and we're going to knock out a bunch of different area formulas. Now, this lesson is designed for you to actually work through it on your own. Directions are laid out, and it kind of walks you through the process for identifying and discovering the different area formulas for triangles, quadrilaterals, and circles. So what I encourage you to do is actually just pause the video here, work through the lesson on your own, and then if you're stuck or if you want to check to make sure you're correct, come back and watch certain parts of the video. But you may not need to watch every part of this video to figure out all the different formulas. So again, I think it's going to be better if you work through it on your own first, and then you come back to the video to just check. That'll help solidify these formulas more in your head than if you just listen to them and write them down. Okay, a lot of these formulas are actually going to be review, but I think a lot of times when you learn them, in middle school or in pre-algebra, you may not have been taught why they are the formulas, like why they work or where they come from, or why the formula for a parallelogram is this and a triangle is this. Is there any relationship? So that's my goal for you through this lesson, is to understand why certain formulas are what they are, rather than just memorizing, different dimensions and numbers. Understand why you're using those dimensions. Area of a parallelogram. This is the first one we're going to look at. To start this, though, we're going to look at the area formula for a rectangle. So this is one we all know, and this is probably one that we were kind of taught why this works. Maybe you used a bunch of blocks on a piece of paper, right? And just did some multiplication, right? So maybe you had, 8 blocks, and you knew that there were 2 for your height and 4 for your width, or 2 for your height, 4 for your base. And if you multiply those together, right, well, you can count off all these blocks to get 8. So the area of a rectangle, I'm going to use base times height. Now, yes, length times width works. They just mean the same thing. Length times width, base times height. Those are the same dimensions for a rectangle. Now, rectangles are a special type of parallelogram. So we're going to see if we can generalize this formula to work for all parallelograms, not just rectangles, right? If we think back to parallelograms, a quadrilateral with 2 sets of parallel sides, a rectangle is a parallelogram with 4 right angles. So let's look at this parallelogram right here. And if you have scissors, you could print out an extra page and actually do this, on your own. I'm going to try to sketch it for you on the screen. But could you make some cuts here and maybe make this parallelogram look like a rectangle instead? Well, yes, we could remove this piece right here and bring it over to this side. If we did that, it would fit nicely in here, and we would have our rectangle. And it just so happens that you could do this for any parallelogram. You can make a cut where you take one side of the parallelogram and move it over to the other side and have the same amount of area, but now it look like a rectangle, which means if we have a rectangle, we could use the rectangle formula. You'll notice that nothing changes here as far as the base and the height of the parallelogram go. Let me just show you real quick. Right, this original base of the parallelogram is going to be the same as the base of our rectangle. Up above, it doesn't change at all. Right, it stays the same. But you're taking this little piece right here, and since you're moving that entire piece over here, the base of the parallelogram stays the same. The height also stays the same as well. And because we know that the correct formula for the area of a rectangle is base times height, well, if we can transform any parallelogram into a rectangle that has the same base and height as the original parallelogram, well, the area of a parallelogram is also going to be base times height. And again, just to reiterate, we would make our cut for the parallelogram right where that line, that segment changes, right? So right where that segment stops, that's where we would make our cut straight down, so forming a perpendicular to the other base, and then we would take this entire triangle and just move it to this side to form our rectangle. So area of any parallelogram is just base times height. Now we do have to be careful. The height of a parallelogram is the perpendicular distance. So again, if I just have this parallelogram, the height is here. The base is here. This segment right here, not the height. Right? The height is going to be the perpendicular distance between the bases, not the slanted distance. So just have to be aware of that. Base times height, with the base or with the height being the perpendicular distance. Okay, moving on to our next one, area of a triangle. You have three sets of triangles here. And again, we have two formulas that we're working with. We have the area formula for a rectangle, base times height, and area formula for a parallelogram, base times height. So if we could transform these triangles into parallelograms or rectangles, well, then we may be able to write a formula for the area of a triangle in terms of what we already know for parallelograms and rectangles. Let me just take this set here first. So if I combine these two triangles, if I move the right one over to the left, it's not fantastic. Let's try that one more time. It's a little better. I could create a rectangle, right, with the same base and the same height as the original triangle. Now, of course, it's twice the size, but it has the same base and the same height as each of the triangles. Now, for these other ones, let's see what we get. So if I move, let's say I move this one down here, I'm also going to have to flip it a little bit. I'm going to have to flip it over. I end up getting something that looks like this. So if I flip that triangle over, rotate a little bit, I could end up building a parallelogram. Notice that the base of this parallelogram is the same as the base of one of the triangles, and the height of the parallelogram is also the height of each triangle. So we formed a rectangle with two of these triangles. We formed a parallelogram with two of these triangles. Let's try it with one more of these. If I move this triangle over here, again, I've got to do some reflections and rotations, but I would get something that looks like this. Again, that is a parallelogram with a base that's the same length as one of the triangles and a height. The height I actually got to draw outside because it's a perpendicular distance. But needless to say, the height of the parallelogram that we formed is the same as the height of both of the triangles. I could keep giving you examples of two congruent triangles, and having you, cut them out and rearrange them into a parallelogram or a rectangle. If they're right triangles, they'll rearrange into a rectangle. If they are non-right triangles, they'll rearrange into a parallelogram. But if I can do that with every set of triangles, well, a triangle ends up just being half of what a parallelogram is. And the base of the parallelogram is the same as the base of the triangle. The height of the parallelogram is the same as the height of the triangle. So let's answer some of these questions down here. We already know the type of polygon we could form each pair of triangles into. That would be a parallelogram. Again, sometimes we can do a rectangle, but a rectangle is still a parallelogram. And since we know that each triangle is just half of the parallelogram that two triangles would form, well, the area of the triangle is 1/2 base times height. And again, this formula comes from the fact that two congruent triangles will always form a parallelogram. All right, moving on to area of a trapezoid, a different type of quadrilateral. So it says, see if you can draw one segment in the trapezoid that splits the trapezoid into two triangles. Because now we have a formula for the area of a triangle, right? So we can use that formula to try to figure out other formulas. Note that the triangles may not be congruent. So let's do that. Let's try to split this parallelogram into two triangles. A couple different ways I can do it. I'm just going to do it like this. Yes, you could have done it like this as well. Either way works. Can we write an expression for the areas of each triangle? Use the variable h for the height of the triangles since they are the same. That is correct. Let me just actually outline these triangles. I'll do one in lime green, one in red, okay, so we have a red and a green, and what's on the paper is correct, right? The heights of both of these triangles, whether it's maybe it's easier to tell for the, whoops. The height of the green, right, is also the same as the height of the red. So the area of triangle 1, let's call the red one 1, the green one 2. So the area of triangle 1 would be 1/2 times the base, which is actually base 2 of the trapezoid, times the height, which is just h. Area of triangle 2 would be 1/2 times base 1 of the trapezoid, because the base of this triangle is up here, times the height, which is just h. Well, if both of these triangles make up the entire trapezoid, well, to figure out the area of the trapezoid, I should just be able to sum those two triangles together. So, and it is on the other page, I'm just going to do it here. Area of the trapezoid is equal to 1/2 base 2 times h plus 1/2 base 1 times h. So this would be the area formula for a trapezoid. However, we can clean it up. We can make it look a little bit more nice by factoring out what is common between both of these terms. Well, what's common is the 1/2 and h. So we can do 1/2 h times a quantity b1 plus b2. Another way you may see this written, b1 plus b2 over 2 times h. But all of these mean the same thing, right? Any of these will get you the area formula for a trapezoid. So what this means is that if you forget the area formula for a trapezoid, right, it's not one that you use that often. So on an ACT, right, they may throw you a trapezoid question dealing with area, and you may not be given the formula for it. Well, almost everyone remembers the formula for a triangle, right? So it's possible that you may have to break the trapezoid down into two triangles to figure out the area of it. But it's possible, right? You could do it based on your knowledge of triangles. And again, it's also cool to understand, okay, why is the formula for a trapezoid 1/2 h times the quantity b1 plus b2? Like, where does that come from? Is it just random? Well, no, it's not random. It's based on the fact we can break any trapezoid down into two triangles. All right, so we did all that up above. Now we are moving on to the area of a kite. So we've had some practice dividing up a polygon into triangles, adding the triangles together to get the whole area of the polygon, and then manipulating a formula to figure out the, area formula for that specific type of polygon or quadrilateral. We're going to do this again to find a kite. So when I draw the diagonals of a kite, I create some triangles. Now, you can either look at this as 4 individual triangles, or you can look at it as two large triangles. Now, again, I'm going to show you the most efficient way to work through this algebra, because depending on which way you do it, the algebra can get a little messy. Oops, let me get my straight line tool here. So I'm going to look at it as this triangle right here in green, and we'll do this triangle here in red. So I'm going to split the kite into those 2 triangles. Now, you'll notice that these diagonals for a kite, one of them is being bisected. And that's this one right here. So that diagonal, D, it doesn't really matter what you call it. It's going to work out the same way. We will assume that this diagonal is D1 and this one is D2. Again, it doesn't matter. They're just arbitrary names for the diagonals. The formula is going to work out to be the same regardless. To figure out the area of this green triangle, well, the base of it is D1. So we'll say area of green so it's 1/2, because it's 1/2 base times height. So 1/2 times D1 times 1/2 of D2. Right? Because the height here is half of the orange D2 diagonal. So area of the green, 1/2 D1 times 1/2 D2. That's going to give us 1/4 D1 times D2. Now the area of the red, very similar, right? Again, 1/2 base times height, so 1/2 D1 times 1/2 D2 gives us 1/4 D1 times D2. So that means the area of the kite is equal to the sum, right? Or you could just do 2 times 1/4 times D1 times D2, right? You could add those together, you could multiply by 2, same thing, which means the area of any kite is 1/2 times one diagonal times the other, right? That will work for any kite. And I'll be honest, this is a formula that I don't remember, right? I rarely use this formula, and I don't expect you to use it very often, but I can figure out what this formula is pretty quickly, right? By breaking the kite down into triangles. So even though I may not remember it off the top of my head in 3 seconds, quickly, knowing what my knowledge is of triangles, I could derive this formula, which means I'm never not going to know it, right? If you just try to memorize all the formulas in this lesson, if you forget one, you're out of luck, right? Because it's just in your brain by memory. if you know how to build the formula, then it can stay with you forever because you can always derive it again or come up with it again, as long as you remember those basic formulas that you use all the time, right? Like the area of a triangle, used way more frequently in your math classes than the area of a kite. All right, I believe we have 2 more. No, we have a lot more. Sorry, whoops, what was I thinking? Moving on to rhombus. Okay, a rhombus is a parallelogram, so you could find it using the regular parallelogram formula, base times height. However, we also have another way of finding the area of a rhombus, which we're going to talk about in this section. But just know that you could always refer back to the parallelogram formula because a rhombus is a type of parallelogram. Sometimes we may not be given the base and the height, though. Then we may have to use this other way. Let's say we are given the diagonals of a rhombus instead. Well, using what we know about the diagonals of a rhombus, namely that they bisect each other, and for a rhombus, both of them bisect each other. Well, we could create some triangles here and kind of do the same thing we did with a kite. Formula may not come out the same, but it's the same idea. So the area of the red. Well, it's a triangle, so we have 1/2 times the base. We're going to call the base of the red D2. So 1/2 times D2 times 1/2 times D1, which again gives us 1/4 times D2 times D1. I think you can see where this is going. The area of the green is the same. 1/2 times D2 times 1/2 times D1 gives us 1/4 D2 D1, which means the area of a kite is 2, because both of these are the same, right? We're adding them together. So 2 times 1/4 times D1 D2, which gives us 1/2 times D1 times D2. So it does end up being the exact same formula for a kite. Take 1/2 of the product of the diagonals. All right, moving on to circles. So we're going to talk about 3 things with circles. We're going to talk about the circumference formula, the area formula, and really what pi represents. Again, some of you may have explored this in a previous class, some of you may not though, and it's good to know, something other than pi just being a bunch of decimal places, right? Or a bunch of numbers that are decimals. So let's take a look at this first activity. This is something you can do on your own. We're going to talk about the relationship between diameter and circumference. So the diameter of a circle just being the longest distance across, and that must go through the center of the circle. So if we're looking at the diameter, here's the center of the circle. The diameter has to go through the center, and it's just that distance right there. The radius would just be half of that, whereas the diameter is the whole thing. So if you find 3 circular objects around your house, you can measure the diameters, write that in the blanks there. Now, this next part you can only do if you have a flexible tape measure that you could wrap around, a circular object. So if you have one, great. If you don't, you may just have to kind of pay attention to what my numbers are and then look for the relationship. But if you have a flexible tape measure, feel free to use it because, doing it hands-on generally helps it sink in a little bit more than just watching and listening. So I'm going to give you some numbers here. I'm actually going to pause the video, fill in the chart, and then we will talk about the relationship. All right, so I just took 3 objects that I had. I measured the diameter and I measured their circumference. And of course, these are not exact. Those are just my best estimates for where it looked like it fell on the tape measure. So I already told you what the relationship we're going to look for is, circumference divided by the diameter. So let's go ahead and do that. And you may want to pause the video here, fill in that last column, and see if you notice anything. So 19 divided by 6, that gives us approximately 3.17. 10.5 divided by 33. 33 divided by 10.5. That gives us approximately 3.14. And 6.3 divided by 2 gives us approximately 3.15. So do we notice anything about those numbers? Well, if you've talked about pi before, right, those numbers look pretty close to what pi is. A lot of teachers end up using 3.14 as an approximation for pi. When you get into upper level classes, you won't use an approximation anymore. You'll actually use the letter pi or the number pi. It's a Greek letter, but it stands for a number. But I digress. And it turns out that in a circle, this relationship always holds true, right? If you divide the circumference by the diameter, you get the same number every time. And that number ends up being pi. So that's where pi comes from, right? It's not just a random number we made up. It's a number that we discovered when, we did a lot of, when we did a lot of research into circles, thousands of years ago. Or I don't know exactly how long it was, but when people were playing around and measuring with circles, when mathematics, was in a much earlier stage than it is now, they made this discovery. And if you think back, actually, way back, this was like the cutting edge of mathematics, right? This discovery of pi. Now, you learn about it when you're in middle school, or maybe even, 5th or 6th grade in elementary school. So it's kind of cool to see how far we've come. The stuff you guys are learning when you're 11 or 12 is stuff that the best mathematicians were just discovering hundreds or thousands of years ago. And this actually leads into what the formula for the circumference of a circle is. If this relationship is always equal to pi, well, if I multiply both sides by the diameter, I get circumference is equal to pi times the diameter. And that is one formula for the circumference of a circle. Another one, because we know that diameter is equal to 2 radii, well, we get pi times 2r. And most of the times you just see it as circumference is equal to 2 pi r. They put the constant out in front, the 2. Even though pi is a constant as well. They just write the numerical constant out front. So again, these are two we want to pay attention to, formulas for finding circumference of a circle. Now let's go ahead and let's talk about how we come up with the area of a circle. Okay, so this was another activity you could do hands-on, but if you cut out 2 circles and you cut them out into little wedges, you were able to form the wedges into this shape right here. And it's not a perfect polygon, right? Because the sides are not segments. They've got some curves. But it certainly looks like a polygon that we've seen before. And you can imagine if you cut those slices into smaller and smaller slices, where this curve became smaller and smaller, right? You could, if you cut those into super small slices, to the naked eye, you would probably not be able to tell that there were curves on the top and bottom bases of this shape, which turns out to be a parallelogram. So that would be the answer, a parallelogram. We know it's not a perfect parallelogram because there will still be some curved edges there, but it gets very, very close. Now, we can also think about, well, what would the height of the figure be? So this height right here, is there a dimension of the circle that is close to what that height of the parallelogram would be? Well, it turns out that this height is pretty close to this length, which is the radius of a circle. So the height of this parallelogram is pretty close to the radius. If we're talking about the length of each base, it's a little tougher to see. But essentially, those bases are made up of the curved edges of those pie slices or pie wedges. And think about what part of a circle, right? So when I cut these wedges out, the curved parts make up what dimension of the circle? Well, they make up the circumference, right? The distance all the way around. But we have to think, right? Half of those curved wedges are for the top base, half of those curved wedges are for the bottom base. So the base, or the bases, are actually equal to 1/2 the circumference, which is equal to 1/2 times 2 pi r, right? 2 pi r was the formula we came up with circumference up above. And then if I simplify even further, I get pi times r. So the bases are approximately equal to pi times the radius of the circle. Now, you may say, Mr. Fawcett, this formula looks okay, but how can it be exact, right? Because this parallelogram that we drew up here, or that we rearranged the pieces into, isn't actually a parallelogram. And, well, you're right, it's not. However, as you cut these slices smaller and smaller and smaller, this parallelogram starts to look more and more like a rectangle where the radius is the height and the base of the rectangle is half of the circumference, or just pi r. And it just turns out, and this is more of a calculus example, and hopefully some of you, I end up getting to teach you calculus in a couple of years when you're a senior. But this has, the idea behind this is a limit. So as you cut these pieces smaller and smaller and smaller, essentially, if you cut them into an infinite amount of pieces, right, which isn't possible because infinity isn't a number. Infinity is just an idea. But as you approach infinity, so as you cut them into more and more and more slices, the answer to the question of, well, if you could cut them into an infinite amount of slices, what would the shape look like? The answer to that question is a rectangle. Now, again, it's more of a calculus idea, so you'll have to take my word for it now until you get to a calculus class and you understand the idea of what a limit is. But essentially, just think about it as, we would eventually get to a rectangle if we could keep cutting these wedges into smaller and smaller pieces. So, whereas you could never do that yourself, think about the idea of that actually occurring. The idea of having an infinite amount of slices, which in that case, you would end up being able to form a rectangle with those two dimensions. Then, right, the area of this rectangle is equal to base times height, which is equal to r times pi r, which is equal to pi r squared. So the area of a circle, and again, this is all, there's space for you to write that down there, but the area of a circle is pi times the radius squared. If you don't quite understand, right, and you don't because you haven't, gotten a lot of practice with the concepts of limits yet. If you don't understand what I was talking about as far as limits and infinity go, that's okay. I just want you to kind of understand the idea, right? And I think we can all understand that if you start to cut a circle up into wedges, you can start to form a parallelogram. And basically, that's where this formula comes from, is that you can start to form a parallelogram, and eventually that parallelogram would look more and more like a rectangle. So base times height, which is how we get pi r squared. One more formula to do. And that is the area of a regular polygon. And obviously we're talking about polygons that are more than 4 sides, because we already know the formulas for, parallelograms, squares, rectangles, trapezoids, etc. So a regular polygon is a polygon where all the angles and sides are congruent. That's important that we realize this formula only works for regular polygons. And we're going to approach it the same way. We're basically going to split the regular polygon up into triangles, find the area of one triangle, and then just multiply that by the total number of triangles in the polygon, which you'll see is equal to the total number of sides. Okay, so let's see if we can figure out the area of one of these one of these triangles. Let me just scroll down a little bit further. Okay, I can't. That's okay. All right, so we already know what the area formula for a triangle is. Area is equal to 1/2 base times height. Here, our base is the length of a side, right? So area equals 1/2 times s. Now, the height of this triangle has a special name. This is called the apothem. This is the distance from the center of a regular polygon to the edge. You can just think about it as the height of the triangle. Again, I just want you to be familiar with the vocab if you see it. An apothem is the distance, the perpendicular distance from the center of a polygon to one of the edges. So our height here, we're just going to call A, which means that the area of this red triangle is 1/2 times the length of a side times the apothem. Now the area of this whole hexagon there's 6 of these triangles, so 6 times 1/2 times s times a is equal to 3 times s times a. So the area of a hexagon, 3 times the length of a side times the apothem. Now, you could just kind of intuitively figure out how to find the area of a pentagon or a decagon or a nonagon, etc. By just multiplying the 1/2 s times a times the number of triangles. There is one other nuance or tidbit here I want to show you, though, and that's if I go back to this right here. Sorry, not this. Let me rearrange this. Let me just draw it again, actually. So this is one formula for the area of a hexagon, but I could actually switch this around. And let me do 1/2 times a times 6 times s. So all I've done is switch around the factors that I'm multiplying together. Well, this 6s, that is the perimeter of the hexagon, right? 6 times the length of one side would give you the perimeter of the hexagon. So one other way that you could write the area of a hexagon. Okay, I really want to figure out why that's occurring because I'm not touching the mouse or anything like that. So got to figure that out. So the area of a hexagon we could also write as 1/2 times the apothem times the perimeter. And it turns out that this actually is the formula for any regular polygon. So it's a formula for a hexagon, but we could also put this in here as regular polygon. Because you got to think, for a regular polygon, this 6s is going to be, it could be 5s, it could be 7s, it could be 8s, it could be 10s, 9s, etc., depending on how many sides there were. But regardless, when you multiply the number of sides by the length of one side, that's going to give you the perimeter. So again, a lot of different ways you can figure out the area to these polygons. And again, I don't expect you to remember all of these formulas. I don't. I'm just trying to show you them, to show you the different relationships between the dimensions, etc. What I do expect you to be able to do is to break down a polygon into triangles or rectangles or squares, etc. In this case, we're doing triangles. Break it down and then use what you know about triangles or another, shape to figure out the total area. So no, don't spend your time memorizing all these formulas. Some are key, right? The rectangle, the triangle, the parallelogram. But basically with all three of those formulas, you can figure out the formulas for any of these other ones. We have gone long enough, but that was a lot to get through. As always, enjoy the rest of your day, and we will come back next time, and we're going to apply some of these equations we have derived today.